And I guess that will be the hardest part for you to manage, because the matrix multiplication, it's a quite unpredictable from your perspective. I don't think you can guess. You will be able to explain why we multiply matrices this way. So look what we do. On the top of my linear operations with matrices, I will introduce matrix multiplication, and that's not an easy operation. It's not going to be done entry by entry. You can multiply matrices entry by entry, but like I said, from the current industry point of view, there is very little value in this kind of operation. Look what we're going to do. If I have a matrix of size, you see, m times n, m rows, m for Mary, n for Nicholas, it's a columns. B, look what the size of B is, n, p. So in that case, if I have two matrices of such sizes, you see the number of columns here is the same as the number of rows here. In that case, and only in that case, I will be able to construct the product which is of some value for the applications, actually of great value for the applications. And the size of the product, it will be another matrix. Look at the size of the product. I take the rows from the first factor, I take the columns from the last factor. Now, if I want to construct the product, I will give the names to the entries of my matrix. Let's just assume that my A has the entries little a, jk. My B has the entries little b, jk. And my AB will have the entries, which I will denote with the letter C. I will show you the direct connection between these numbers and these numbers. Formal connection is like this. Formal connection is like this. Look what's happening. Every entry, CJK, in my product is formed by this long sum. Here's the expansion for this sum. Here's the expansion for this sum. I think the best way to grasp the idea of the multiplication is by the example. I'll show you one example, and you will see why how this sum works. In fact, well, if you want some comments on this, look what happens here. I take look at this. All of the A's here across this sum, all of the A's, they have identical first index j, which means they come from the same row, jth row. All of the B's across this sum, they have identical second index, k, which means they come from the same column, k, in the B matrix. So basically, this looks like a dot product, isn't it? So what you're looking here at is the dot product of the jth row and the kth column. If you think of them as vectors, dot product of the jth row of the matrix A and the kth column of the matrix B. If you take such a dot product, that will be the CJK element of my original matrix. Look at this. Here's the example. Again, my identical, the same two matrices, A and B, from my previous example. So you don't have to copy this. Here's my A and B. I will construct the product of these two. Sorry, I have to lower this. Here's my indices Mn. Here's my indices Np. So at least from the point of view of the dimensions of these matrices, they are compatible. You see the number of rows here, 3, is the same as the number of, I said rows, I mean columns. The number of columns here is the same as the number of rows here. So my AB matrix, it will be of size MP, so it will be 3 times 2 matrix. Well, I have it here pre-computed already. I will open it, and I will comment on every entry after that, because I cannot do it right now. I cannot do it in any other way. Look at this. I claim that the product will be like this. Let's just try to see this. First entry, 7. The indices for the first entry is 1 and 1, right? J1, K1. According to what I said before, if I want to find this element, I have to take the dot product of the first row here and the first column here as vectors. Here it is. 5 times 2, 3 times 5, 9 times negative 2. If you perform this arithmetic, 10, 15, take 18, it is 7, right in here. If I want to convince you that this element will be 48, this is the element with the indices 1, 2, which means I have to take the dot product of the first row and the second column. Here is the dot product. 5 times negative 3, 3 times 9, 9 times 4. This one is negative 15 plus 27, it's plus 12, plus 32, it's 36, sorry, 30, it's 48. So far, so good. You can do this check, and in fact, every time you multiply these matrices, you will do this dot product for every entry. There's no any other way to do that. It's very computational intensive task, finding the product of two matrices. It's just that's the way the life is, and you have to live with this. I mean, you may say, why don't we multiply the matrices in the per component way? You may have such an argument, but that's a very naive argument. And I don't have any response to that, in fact. All I can tell you that for the applications, the industry, and everyone else, that product doesn't represent any value. It's easy to compute, but the value of that product is 0. Whereas this one is hard to compute, and the value of this product is great. So, for instance, if I want to check this element, say negative 8, for instance, I should take, what's the indices for this element in the resulting matrix? It's 3, 1, third row, first column. So I take the dot product of the third row and the first column. Double check. I don't have the pre-type double check. I'll just do it from the top of my head. 8 times 2, 16. Negative 4 times 5, it's negative 20, so it's negative 4. And 2 times negative 2, it's negative 4 again, so it's negative 8 altogether. And that's how we multiply